Chapter 1: The Internet, the World Wide Web and HTTP. To harness the web, you need to understand its foundations and design. We start our journey toward web APIs at the beginning. In the late 1960s, the Advanced Research Projects Agency network ARPANET, a series of network-based systems connected by the TCP/IP protocol, was created by the Defense Advanced Research Projects Agency DARPA. Initially, it was designed for universities and research laboratories in the US to share data. See Figure 1:1. ARPANET continued to evolve and ultimately led in 1982 to the creation of a global set of interconnected networks known as the Internet. The Internet was built on top of the Internet Protocol Suite, also known as TCP/IP, which is a collection of communication protocols. Whereas ARPANET was a fairly closed system, the Internet was designed to be a globally open system connecting private and public agencies, organizations, individuals, and institutions. In 1989, Tim Berners-Lee, a scientist at CERN, invented the World Wide Web, a new system for accessing linked documents via the Internet with a web browser. Navigating the documents of the web, which were predominantly written in HTML, required a special application protocol, the Hypertext Transfer Protocol (HTTP). This protocol is at the center of what drives websites and web APIs. Figure 1:1. ARPANET image from Wikimedia Commons. In this chapter, we'll dive into the fundamentals of the web architecture and explore HTTP. This will form a foundation that will assist us as we move forward into actually designing web APIs. Web architecture. The web is built around three core concepts: resources, URIs, and representations, as shown in Figure 1:2. A resource has a URI that identifies it and that HTTP clients will use to find it. A representation is data that is returned from that resource. Also related and significant is the media type, which defines the format of that data. Figure 1:2. Web core concepts. Resource. A resource is anything that has a URI. The resource itself is a conceptual mapping to one or more entities. In the early years of the web, it was very common for this entity to be a file such as a document or web page. However, a resource is not limited to being file-oriented. A resource can be a service that interfaces with anything such as a catalog, a device e.g., a printer, a wireless garage door opener, or an internal system like a CRM or a procurement system. A resource can also be a streaming medium such as a video or an audio stream. Is a resource bound to an entity or a database? A common misnomer today with web APIs is that each resource must map to an entity or business object backed by a database. Often, this will come up in a design conversation where someone might say, "We can't have that resource because it will require us to create a table in the database, and we have no real need for a table." The previous definition described a mapping to one or more entities. This is an entity in the general sense of the word, i.e., it could be anything, not a business object. An application may be designed such that the resources exposed always map to business entities or tables, and in such a system the previous statement would be true. However, that is a constraint imposed by an application or framework, not the web. When you are building web APIs, there are many cases where the entity/resource constraint is problematic. For example, an ordered processing resource actually orchestrates different systems to process an order. In this case, the resource implementation invokes various parts of the system that may themselves store state in a database. It may even store some of its own state, or not. The point is there is not a direct database correspondence for that resource. Also, there is no requirement that the orchestrated Components use a database either, though in this case they do. Keep this distinction in mind as you go forward in your web API design. It will help you to really harness the power of the web within your systems. URI, as was mentioned earlier, each resource is addressable through a unique URI. You can think of a URI as a primary key for a resource. Examples of URIs are http://fabry kam.com/orders/100, http://ftp.fabricam.com, mail to john.doexample.com, telnet// 192.168.1.100, and Ernest 978-1-449-33771-1. A URI can correspond only to a single resource, though multiple URIs can point to the same resource. Each URI is of the form scheme. Hierarchical part, query fragment with the query string and fragment being optional. The hierarchical part further consists of an optional authority and hierarchical path. URIs are divided into two categories, URLs and URNs. A URL universal resource locator is an identifier that also refers to the means of accessing the resource, while an URN universal resource name is simply a unique identifier for a resource. Each of the preceding example URIs is also a URL except the last one, which is a URN for this book. It contains no information on how to access the resource but does identify it. In practice, however, the majority of URIs you will likely see will be URLs, and for this reason the two are often used synonymously. Query string or not. One common area of debate is whether or not you should use query strings at all. The reasoning for this has to do with caches. Some caches will automatically ignore any URI that has a query string in it. This can have a significant impact on scale, as it means all requests are directed to the origin server. Thus, some folks prefer not to use query strings and to put the information into the URI path. Google recommends http://bit.ly/ Optimize cache not using query strings for static resources that are cacheable for the same reason. Cool URIs. A cool URI is a URI that is simple, easy to remember, like http://www.example.com/ people/Alice, and doesn't change. The reason for the URI not to change is so it does not break existing systems that have linked to the URI. So, if your resources are designed with the idea that clients maintain bookmarks to them, you should consider using a cool URI. Cool URIs work really well in particular for web pages to which other sites commonly link, or that users often store in their browser favorites. It is not required that URIs be cool. As you will see throughout the book, there are benefits to designing APIs without exposing many cool URIs. Representation. A representation is a snapshot of a resource's state at a point in time. Whenever an HTTP client requests a resource, it is the representation that is returned, not the resource itself. From one request to the next, the resource state can change dramatically, thus the representation that is returned can be very different. For example, imagine an API for developer articles that exposes the top article via the URI http://devarticles.com/articles/top. Instead of returning a link to the content, the API returns a redirect to the actual article. Over time, as the top article changes, the representation via the redirect changes accordingly. The resource, however, is not the article in this case. It's the logic running on the server that retrieves the top article from the database and returns the redirect. It is important to note that each resource can have one or more representations, as you will learn about in content negotiation on page 17. Media type. Each representation has a specific format known as a media type. A media type is a format for passing information across the internet between clients and servers. It is indicated with a two-part identifier like text/HTML. Media types serve different purposes. Some are extremely general purpose, like application/JSON, which is a collection of values or key values, or text/HTML, which is primarily for documents rendered in a browser. Other media types have more constrained semantics like application/ATONXML and application/collection JSON, which are designed specifically for managing feeds and lists. Then there is image/PNG, which is for PNG images. Media types can also be highly domain specific, like text/vcard, which is used for electronic sharing business card and contact information. For a list of some common media types you may encounter, see Appendix A. The media type itself actually comprises two parts. The first part before the slash is the top-level media type. It describes general type information and common handling rules. Common top-level types are application, image, text, video, and multi-part. The second part is the subtype, which describes a very specific data format. For example, in image/PNG and image/GIF, the top-level type tells a client this is an image, while the subtypes PNG and GIF specify what type of image it is and how it should be handled. It is also common for the subtype to have different variants that share common semantics but are different formats. As an example, HAL hypertext application language has JSON application/HAL JSON and XML application/HAL XML variants. HAL JSON means it's HAL using a JSON wire format, while HAL XML means the XML wire format. The origin of media types. The earliest roots of media types are with ARPANET. Initially, ARPANET was a network of machines that communicated via simple text messages. As the system grew, the need for richer communication arose. Thus, a standard format was codified for those messages to allow them to contain metadata that related to processing. Over time and with the rise of email, this standard evolved into MIME, the multipurpose Internet Mail Extensions. One of the goals of MIME was to support non-textual payloads, thus the media type was born as a means to describe the body of a MIME entity. As the Internet flourished, it became necessary to pass similar rich bodies of information across the web without being tied to email. Thus, media types started being used to also describe the body of HTTP requests and responses, which is how they became relevant for web APIs. Media type registration. Media types are conventionally registered in a central registry managed by IANA, the Internet Assigned Numbers Authority. The registry itself contains a list of media types and links to their associated specifications. The registry is categorized by top-level media types, with each top-level section containing a list of specific media types. Application developers who want to design clients or servers that understand standard media types refer to the registry for the specifications. For example, if you want to build a client that understands image/PNG, you can navigate to the image section of the IANA media types pages and find PNG to get the image/PNG spec, as shown in Figure 1 to 3. Figure 1 to 3. IANA registry for image. Why do we need all these different media types? The reason is because each type has either specific benefits or clients to which it is tailored. HTML is great for laying out documents such as a web page, but not necessarily the best for transferring data. JSON is great for transferring data, but it is a horribly inefficient medium for representing images. PNG is a great image format, but not ideal for scalable vector graphics. For that, we have SVG. TOM, HAL, and collection JSON express richer application semantics than raw XML or JSON, but they are more constrained. Up until this point, You've seen the key components of the web architecture. In the next section we will dive into HTTP glue that brings everything together. HTTP. Now that we have covered the high-level web architecture, our next stop is HTTP. As HTTP is very comprehensive, we will not attempt to cover everything. Rather, we will focus on the major concepts, in particular, those that relate to building web APIs. If you are new to HTTP, it should give you a good lay of the land. If you are not, you might pick up some things you didn't know, but it's also okay to skip it. HTTP is the application-level protocol for information systems that powers the web. HTTP was originally authored by three computer scientists, Tim Berners-Lee, Roy Fielding, and Henrik Frystyk Nielsen. It defines a uniform interface for clients and servers to transfer information across a network in a manner that is agnostic to implementation details. HTTP is designed for dynamically changing systems that can tolerate some degree of latency and some degree of staleness. This design allows intermediaries like proxy servers to intercede in communication, providing various benefits like caching, compression, and routing. These qualities of HTTP make it ideal for the World Wide Web, as it is a massive and dynamically changing and evolving network topology with inherent latency. It has also stood the test of time, powering the World Wide Web since its introduction in 1996. Moving beyond HTTP 1.1, HTTP is not standing still, it is actively evolving both in how we understand it and how we use it. There have been many misconceptions around the HTTP spec RFC 2616 due to ambiguities, or in some cases due to things deemed incorrect. The IETF Internet Engineering Task Force formed a working body known as FBBs that has created a set of drafts whose sole purpose is to clarify these misconceptions by completely replacing RFC 2616. Additionally, the group has been charged with creating the HTTP 2.0 spec. HTTP 2.0 also does not affect any of the public HTTP surface area. Rather, it is a set of optimizations to the underlying transport, including adoption of the new SPDY protocol. Because FBBs exists as a replacement for the HTTP spec and provides an evolved understanding of HTTP, we'll use that as the basis for the remainder of this section. HTTP message exchange. HTTP-based systems exchange messages in a stateless manner using a request/response pattern. We'll give you a simplified overview of the exchange. First, an HTTP client generates an HTTP request, as shown in Figure 1-4. Figure 1-4. HTTP request. That request is a message that includes an HTTP version, a URI of a resource that will be accessed, request headers, an HTTP method like GET, and an optional entity body. Content. Key request is then sent to an origin server where the resource presides. The server looks at the URI and HTTP method to decide if it can handle the message. If it can, it looks at the request headers that contain control information such as describing the content. The server then processes the message based on that information. After the server has processed the message, an HTTP response, generally containing a representation of the resource as shown in Figure 1-5, is generated. Figure 1-5. HTTP response. The response contains the HTTP version, response headers, an optional entity body, containing the representation, a status code, and a description. Similar to the server that received the message, the client will inspect the response headers using its control information to process the message and its content. Intermediaries. Though accurate, the preceding description of HTTP message exchange leaves out an important piece: intermediaries. HTTP is a layered architecture in which each component Component/server has separation of concerns from others in the sitem. It is not required for an HTTP client to see the origin server. As the request travels along toward the origin server, it will encounter intermediaries, as shown in Figure 1 to 6, which are agents or components that inspect an HTTP request or response and may modify or replace it. An intermediary can immediately return a response, invoke some sort of process like logging the details, or just let it flow through. Intermediaries are beneficial in that they can improve or enhance communication. For example, a cache can reduce the response time by returning a cached result received from an origin server. Figure 1 to 6. HTTP intermediaries. Notice that intermediaries can exist anywhere the request travels between the client and origin server. Location does not matter. Hey can be running on the same machine as the client or origin server or be a dedicated public server on the internet. Hey can be built in, such as the browser cache on Windows, or add-ons commonly known as middleware. ASP.NET Web API supports several pieces of middleware that can be used on the client or server, such as handlers and filters, which you will learn about in Chapters 4 and 10. Types of intermediaries. There are 3 types of intermediaries that participate in the HTTP message exchange and are visible to clients. A proxy is an agent that handles making HTTP requests and receiving responses on behalf of the client. Client's use of the proxy is deliberate, and it will be configured to use it. Is common, for example, for many organizations to have an internal proxy that users must go through in order to make requests to the internet. A proxy that modifies requests or responses in a meaningful way is known as a transforming proxy. A proxy that does not modify messages is known as a non-transforming proxy. A gateway receives inbound HTTP messages and translates them to the server's underlying protocol, which may or may not be HTTP. The gateway also takes out bound messages and translates them to HTTP. A gateway can act on behalf of the origin server. A tunnel creates a private channel between 2 connections without modifying any of the messages. An example of a tunnel is when 2 clients communicate via HTTPS through a firewall. Is a CDN an intermediary? Another common mechanism for caching on the internet is a content delivery net. Work CDN, a distributed set of machines that cache and return static content. There are many popular CDN offerings, such as Akamai, that companies use to cache their content. So is a CDN an intermediary? The answer is that it depends on how the request is passing to the CDN. If the client makes a direct request to it, then it is acting as an origin server. Some CDNs, however, can also act as a gateway, where the client does not see the CDN, but it actually acts on behalf of the origin server as a cache and returns the content. HTTP methods. HTTP provides a standards